Okay, so lectures on Koopman operator methods in dynamical systems. So this is ME203 for winter 2022. And let's start with a little bit of an overview of what we're going to talk about in this lecture and maybe a few next lectures. We'll discuss points of view in dynamical systems theory with a view that we're going to introduce the Koopman operator approach right after that. Then we're going to spend some time talking about Koopman operator eigenfunctions. And in particular, we are going to be interested in some of what is called algebraic properties of Koopman eigenfunctions. The interest here is to understand why is this approach that in principle represents a nonlinear system with an infinite dimensional linear system still in some sense and in some contexts a finite theory that you can compute with finite number of objects. So we'll very early kind of deal with that particular issue that it seems like maybe we are introducing a lot of complexity in the picture. Then we're going to talk about something that's called the Koopman generator, or the generator of the dynamics. And that is specifically for the smooth evolution. Smooth evolutions. You will see that this framework is capable of handling non-smooth dynamical processes as well. But we will concentrate here on dynamical systems coming from smooth maps and flows, and that's for the purpose of simplicity a little bit at the beginning. There's a concept that in the previous classes on dynamical systems you probably didn't see, and that is the concept of partitions of state space. It plays a very prominent role in this particular theory and provides you a slightly different point of view on the geometry of dynamical systems. And then we'll go through some aspects of asymptotic dynamics. In particular, we are going to treat some non-trivial asymptotics like limit cycle attractors, quasi-periodic attractors, and chaotic attractors. The dynamics can be split into asymptotic and transient, and so the next aspect we're going to talk about is transient dynamics. And that's going to be all the content of this introductory set of ideas that we have here. So what I'm going to do next is summarize a couple of mathematical approaches. For those of you that have taken 215, you've seen some of this, but I'll just review them and refresh them, and then jump right into the operator theoretic approach, and then right after that, talk about partitions. So let's get going. Historically, there are really three major points of view in dynamical systems theory. One of them is value versus time. I call it Newton's point of view that, of course, originated when Newton worked out the ideas of calculus, and then followed up with the theory of gravity that involved setting up physical laws as second order ordinary differential equations. And if you could find a solution of that ordinary differential equation, then you would usually plot it as value, which could be position or momentum of a system versus time. So a little bit of notation. If x of t is a vector in Rn that changes with time t, then x dot is f of x and t is going to be an ordinary differential set of ordinary differential equations, and f of x and t is a time-dependent vector field. F would have to satisfy certain properties for the solutions of this system to exist. In particular, you have to have Lifshitz continuity for existence and uniqueness. If we restrict to the situation where the system is autonomous, we would get x dot is equal to f of x. And it would be quite valuable that we obtain x as a function of time here, plug it into the left and the right side. And if they're equal, that's a solution. Provided we give it an initial condition x of 0, that's a solution starting from some initial condition. And solving for x as a function of time then leads to this evolution. I wrote this as a map. So x of t is really a map from some initial condition x0 to time t. Since there is time involved in the description, we can also label this object or this map with t as a superscript and have st of x0, which is really just a map from some x0 at time t. So it tells you the position in space Rn that the system has acquired starting from x0 at time t pictorially. I think I have a picture of this somewhere. Give me just a second. So you start from x0, and this trajectory in state space takes you to some later position at time t. All right. So, so this object here is called the flow, and it's really just a one-dimensional family of maps that take a set of initial conditions and provide their position some later time t. If we have time dependence, then that flow here should be labeled with 2 instances of time. So you start at x0 at t0, and you land at time t at some other position, which we labeled with x of t, t0, and x0. So this would be the non-autonomous version. You will see that in this class, we will mostly deal with the autonomous version that is labeled just with one time. And the reason for it being labeled with just one time instance is that for an autonomous system, the evolution from time 0 to time t is exactly the same mapping from the same x0 as if you would start from delta t and go to t plus delta t. That's the basic idea. All right, so simple example, if you have a mass spring system and you have a free, undamped, 1 degree of freedom vibration system, mx double dot is equal to minus kx. This just means that I have a linear spring that is providing a force that is negative k, which is the stiffness times x. One can solve this equation explicitly to obtain position as a function of time and initial conditions. What are initial conditions? In this case, it's x of 0 and x dot of 0. There's a little bit of abuse of notation because, of course, in the previous case, we had x as a vector, dot is equal to f of x. So, x of 0 here was labeled with x0. I have to recognize that we have the position and velocity that are important quantities in this physical evolution. And therefore, I have x of 0 and x dot of 0 as initial conditions. In a second, I will present a state space picture of this. And of course, then I could call x dot y. And in this context, y of 0 would be the element of that bold x vector that I had before. But having stated that, we have a function, so x of t, of time that depends on also initial conditions. And those initial conditions are 2. One is in position, one is in velocity. And in this way, we would know the position starting from some initial velocity, and some initial condition for all time. And here is the evolution for displacement or position and velocity for some given time between 0 and 2 for a particular stiffness of 50 newtons per meter. And and some specific initial conditions and frequencies. And so these two top ones are plots of position versus time and velocity versus time. This one on the bottom here is really the plot of position versus velocity. And that approach seems somewhat, let's say, obvious and maybe not containing too much information. Maybe it's even losing information because the plot of position versus velocity tells you that you're going, let's say, from some initial position at 0 with certain velocity, let's say it's 1, and then you proceed to the furthest out position with the spring mass system to the right, and then the velocity decays, or rather it's negative, and then you pass through the origin with the highest velocity, negative velocity, go back to the left, and then return back to the top. Obviously, if I ask, well, at which time have I reached this? I don't have that information. So this is velocity versus time. This is position versus time. This is position versus velocity. That's a numerical plot of how the system executes this. And this is called a state space representation. And as I said, in this case, it seems like we've lost a little bit. Yes, we've lost a little bit. We've lost the information on time, but we actually gained quite a bit as well. And that's something that Poincaré realized in 1890. There was a realization that x dot is equal to f of x cannot always be solved in a closed form. In particular, the study was of the three-body problem. Think Sun, Earth, Moon. So Sun, Earth, you all solved for in undergraduate classes or graduate classes. It reduces to a second-order ordinary differential equation that can actually be solved and gives us those elliptic, parabolic, hyperbolic trajectories. So it can be explicitly solved despite the fact that the system is actually non-linear. The system for the spring mass was linear because it had only the first power of the position, on the right-hand side. Yeah, so that was linear. The system that occurs in planetary dynamics is non-linear because the law of gravity has that 1 over r, the inverse of the distance, in it, and that's a non-linear function. And it was realized by Poincaré that when you work on such a three-body problem, you cannot really write down the position versus time and momentum versus time in a closed form. And he even surmised that you could get very, very complex solutions in time from that. So in some sense, he had intuition that something like chaotic behavior that we spoke about a little bit in 215, things like Lorentz attractor could be there, very specifically actually because he was working on conservative, non-dissipative systems. For him, it was more separatrix scales that I'll describe a bit when we go to discussing operator theoretic approach to chaotic systems that are in fact conservative or measure preserving. I'll say quite a bit more about that a bit later. But the realization that Poincaré had was that instead of trying to find these closed solutions, you can say a lot about the system by understanding the right-hand side of first-order equations. So Newton's equations were second-order. Poincaré realized that if you define a new variable, for example, y, that is itself just the velocity. In fact, in physics, you should usually go with a canonical variable, and that's momentum rather than velocity. But for the sake of simple description, let's talk about velocity being a new variable. Then you can put it in state space, x dot is equal to y dot is equal to minus k over mx. And that's something that you need to do anyhow. For example, if you want to simulate these equations using, let's say, Runge-Kutta in software like MATLAB, is going to require you to put it in the first order system form. But an important thing is that Poincaré realized that the right-hand side of this can be thought of as a vector field. So there are a couple of interesting things in this. One is that Poincaré realized that first order equations, if you write your equations in first order, which you can always do for any higher order set of ordinary differential equations, defining new observables is in fact something useful, because you can look at the right-hand side, plot it as a vector field like we did in these prerequisite classes, and get qualitative understanding of what ensues. In some sense, you get a lot of qualitative understanding of dynamical systems using this, and it can, in principle, be done for systems that are not solvable in closed form very often, right? So what are the concepts that we learned from this advance? Well, one of them was that very special solutions of our vector fields are meaningful to study and carry a lot of information about the system itself. So for example, if you find the points for which f of x is equal to 0 for our system of ordinary differential equations, then you get fixed points, and fixed points are important. They are the points in state space for which the state of the system doesn't change. And of course, you can do stability analysis around them, understand whether it's a stable fixed point. If it is, for example, it attracts nearby solutions, and you know that asymptotically solutions are going to go towards the fixed point. So you learn something about the dynamics from simple discovery of algebraic discovery of fixed points, and then the later linearizations-based study of their stability. Now, more complicated solutions are periodic orbits. They have those for which you start at some time t, at some later time capital T, you get back to the initial point. Stability of these can be studied as well. Another important class of solutions is stable and unstable manifolds. So stable manifolds being sets of points such that starting from any such point, when time goes to infinity, the solution of my ordinary differential equation goes to x being the fixed point in this example. As time goes to infinity, that'll be a stable manifold. And then if you ask for convergence when time goes to minus infinity, you get the idea of the unstable manifold. So all of these quote unquote special solutions of ordinary differential equations were not understood to be as important as they really are before Poincaré. So this qualitative state space methods brought up the focus on asymptotics and the stability of that asymptotic behavior. But 60, 70 years pass until some of the full potential of that picture was realized with now very famous Lorentz discovery of a physically motivated system with aperiodic asymptotic dynamics. It is rarely pointed out, but very true, that at Kyoto University, Ueda, in fact, in 1961, found experimentally an object that turned out to be a strange attractor in an electronic circuit that he was studying. So this discovery of the unusual non-periodic, so none of these, or rather none of the simplicity of these solutions held, So non-periodic solutions of ordinary differential equations actually goes to Ueda and then Lorentz. So as we have seen, in this point of view, value versus time are replaced with relationship between state variables, and sometimes you're required to define new state variables. So in the language we're going to use in this class, you actually define new observables, such as me defining velocity as a new observable for the mass spring system, in order to understand the dynamics. And this seems like it obviously brought a lot of understanding of dynamical systems, and this whole conceptual framework basically penetrated any mathematicized science that we know of. It's obviously used a lot in physics, a lot in biology, in system biology in particular, even in social sciences in the last couple of decades, quite a bit, where people write down differential equations or a different type, maybe discrete time dynamical system, in order to model the behavior and then study it using the tools that Poincaré's advances brought us. And then, of course, 130 years of development in between put the whole theory on extremely solid mathematical foundations. So big success, geometric dynamic. This is basically what is in modern terms a geometric dynamical systems theory. But it's an approach that currently faces some pretty serious hurdles. We can do extremely well understanding systems in 2 and 3 dimensions, and in special cases 4, 5, 6, maybe 3 degrees of freedom, So the 3-body problem is still investigated in gory detail. That's Poincaré's problem from 130 years ago. There are still papers that are studying that problem, and really, really good papers, by the way, with very solid mathematical results that are studying that problem from this perspective. But the theories that it provides are usually hard to extend to very high dimensions. Geometry of high dimensional systems is hard, let's put it that way. Even if you start thinking in 4D, it becomes hard. So space and time becomes hard, right? Let alone if you're trying to think in state space of 20, 30 dimensions or more. And the other part is that the science has become incredibly data rich. I mean, in Newton's time, the data was sparse. The kind of discovery that he made was based on understanding of Kepler's laws, understanding of the available data on celestial mechanics. But even that was pretty sparse. I mean, that was not a very rich source of data. The discoveries that Einstein did in general relativity relied on almost no data. There was only the understanding that the planet Mercury has an odd orbit that does not exactly conform to Newton's laws. So that theory came from an extremely small amount of data. Quantum mechanics at the beginning, if you think about the most, the theories that we use in engineering today, and yes, we do use general relativity. Your GPS system cannot quite operate as accurately as it should without the use of GPS. And in engineering in general, quantum mechanics is becoming one of the dominant research fields from an engineering point of view for quantum information processing, things like that. So those are the theories. Even quantum mechanics, to start with, relied on small amounts of spectral data that scientists possessed. Now we live in a very different world. There massive amounts of data generated all the time. And the problem is sort of an opposite problem. While historically the theories that we formed relied on extracting or extrapolating from very small amounts of data, and trying to figure out general laws, and there were serious mistakes being made by some of the most prominent scientists in all history, right? Galileo himself thought that forces that velocity is proportional to force, not acceleration, right? So that's because they relied on small amounts of data, and Galileo's world was dominated by friction. He studied friction quite a bit, although he studied celestial dynamics as well. Today's problems are different. We have massive amounts of data, and that also means massive amounts of noise, where patterns need to be extracted from that multidimensional data in order to try to find laws within them. It's a different problem, maybe, a somewhat better problem to have. And that's what machine learning, all the approaches in machine learning are trying to resolve. So I'd like you to view the operator theoretic approach, despite the fact that I'm going to talk mostly about theorems and mathematical results. I'd like you to view it as a way of extracting patterns and formulating models of behavior from data. And in some sense, for this approach, the more data, the better. But it has capabilities to filter the data for meaning in some sense. And that's why it's really kind of a learning methodology, and why it's used in a variety of contexts to model systems from data. So even if you look at the Poincaré point of view, you're going to find some elements of this, slightly more modern point of view that I'm going to present next. Slightly more modern because it was really devised at the end of 20s, beginning of 1930s. Not in the context of data analysis, but in the general concept was there. So if you think about trying to understand data in general, trying to understand a dynamical system, one of the things that you would like to know is anything invariant under the motion? So all of you have background in physical sciences, largely. Is there anybody with neuroscience or biology background here? A little bit, okay. So all of you have background in physical sciences, and if we find an invariant, for example, energy, that turns out to be an important quantity in whatever point of view you'd like to view it at. So how do we find an invariant for a system x dot is equal to f of x, just a system of ordinary differential equations? Well, h, which is a function of x, is an invariant provided it doesn't change in time. Right? If you take a look at the frictionless mass spring system, the amount of energy in the system is split between potential and kinetic energy, but the sum of those two is always the total energy, and that never changes in time, whatever the system does. And the mathematical equation for this is that grad h, which represents the change in h, so this is the vector of partial derivatives of h with respect to the underlying variables, dotted with f. So this would be read as this is from your multi-dimensional multivariable calculus. So this is the change of a function h, which is a function of x, in the direction of a vector f is equal to 0. So that's an equation. If you solve this equation knowing f, that's going to give you an invariant. What is interesting here is that you can solve this equation without ever solving for x dot is f of x in terms of x, right? The solution of it depends only on knowing f. It's a partial differential equation. I'll give you an explicit example below here. But the point is, this is kind of Poincaré's point of view. You will see in a second that it's because only the right-hand side of the vector field is being necessitated for the solution. It is also an operator theoretic point of view. I'll show you this as we go forward, because this equation has a very prominent meaning in an operator theoretic approach. I want to stress out that the interplay between the Poincaré view and the operator theoretic point of view is all-encompassing, in the sense that one can, in my view, only understand the subject well, provided one understands well both sides of the coin. So both what the operator theoretic aspect brings to the table and what the geometric aspect brings to the table. So brush up your ME203 notes, or you know, Steve Strogat's book, or Steve Ignis's book, whichever one is your favorite book on the background on geometric theory, because we are going to rely on that quite a bit. So let me point out another important concept. So suppose you found this function h, then find the sets on which h is constant. Those define invariant sets, correct? Right? The invariant sets are the sets that if the dynamics in state space starts in them, then it never leaves them. But if h is constant, so h dot is equal to 0, then the trajectory cannot leave. If trajectory starts in that set, it cannot leave it, because that would mean that h is not constant, and therefore I would have a contradiction. So QED, the level sets, so sets on which h is constant, actually define invariant sets. This is a prequel of the notion of a partition. We'll talk a lot about the partitions, geometric partitions of state space that we are going to obtain using operator theoretic methods. The partition here is in the levels of constant values of an invariant. Now, let's go through an example. I think it's going to become a little bit clearer. So take the mass spring system. What you're seeing here is an h. That's a function of x and x dot, or as you remember, I defined x dot as y in the Poincaré picture. 1/2 x dot squared plus k over m x squared. That would be kinetic energy divided by mass plus potential energy. There is a 1/2 multiplying it. Potential energy divided by mass, right? So we all know already that h is an invariant. How do we get it from this equation? Well, here, h dot is partial h with respect to x, x dot, plus partial h with respect to x dot, y dot. That's x double dot. Remember, x dot is y, x double dot is y dot. Now that's partial h with respect to x. X dot itself, take a look, is partial h with respect to x dot. Take a look at the differentiate this with respect to x dot, and you're going to find that that's just x dot. And then partial h with respect to x is k over m x. And then you have partial h with respect to x dot copied over here. But look, that's partial h with respect to x, partial h with respect to x dot, minus partial h with respect to x dot, partial h with respect to x. That's symmetric, and with a minus in the middle, and so that's 0. So what do I have here? Well, this equation here is precisely that equation, because my f consists of two components. One of them is y, which is just x dot, and one of them is minus k over m x. Let me remind you of that. So my capital F consists of two components, y and minus k over mx, right? So when you plug those in here, those two in here, you get a 0, and therefore, observing that the value of this energy per mass is some constant c, the equation here, so that being equal to some c, is just an equation for an ellipse. So an ellipse is precisely what seems to be plotted here for a trajectory of a dynamical system. So my larger point is, in order to obtain that solution of a dynamical system, we can start with solving a partial differential equation, find h, and then plot the level sets and get geometry. So get what the trajectory looks like from the solution of a partial differential equation. Now, here is what you might be thinking. Well, didn't you just make the problem harder because you asked me to solve a partial differential equation when I started with ordinary differential equations? To some extent, yes, but the benefit is large. The finding an invariant is a big deal. If you just Google energy, literally you will see, I don't know how many hits, probably uncountable, even today, right? So once you find invariants of a dynamical system, that's a very, very big deal. It gives you invariant sets, and even it can even enter popular context. I believe it was Bernoulli who integrated Newton's equations and found that energy is, as an integral of motion is conserved, and that's where the whole diverse set of uses of the word today stem from. So the larger point is, you see how solving what is in principle an infinite dimensional dynamical system for h instead of solving the original system gives you benefit, and that's conceptually what we are going to be doing. We're going to, in this whole operator theoretic approach, very commonly ask for solutions of an equation that is not precisely just like that, a more generalized form of this. And then we'll say that if we find something like h, an invariant, or other types of functions that solve these kinds of equations, you will see a lot of physical meaning stemming from those. That's kind of conceptually where we're going to go. Now, there is another approach to dynamical systems explored a lot in the theory of vibrations and in theory of control, and that has a long history. I called it the Wieners Picture because Norbert Wiener at MIT, and especially during the Second World War, and then when he wrote his book Cybernetics, that's where the word stems from, cyber, right? He made the largest advances, including writing a book called Generalized Harmonic Analysis that tells you how do you deal with processes and signals that have aperiodic nature. How do you deal with them still within the context of harmonic spectral analysis? And it has some very salient features that are quite interesting from a modern point of view. First of all, you just collect data. So think of the simplest version of this as just taking data and doing a fast Fourier transform on the data and obtaining some core frequencies at which the system oscillates. there is no model like the mass spring model necessary. You're just taking the data and analyzing the system directly from data. And another aspect that is really interesting is that it has ability to compress the knowledge pretty dramatically. So sometimes I joke about this in the context of machine learning as being the first autoencoder. We have a fancy name for things that compress a lot of different data into a smaller set, perhaps somewhat aggregated autoencoders. But in fact, I'll show you on an example that, of course, the frequency analysis is, in fact, an example of this. So let's take our spring mass system again. And let's take the solution x of t in its harmonic form. We can always put the solutions look something like this. And so you can always put it in the context in which you have amplitude, and then the frequency, natural frequency, and then the phase. But the nice thing is that if you could somehow extract amplitude, natural frequency, and phase from a signal, then you have the ability to reconstruct the whole signal without explicitly knowing its time dependence with 3 numbers: amplitude, frequency, phase, right? In Newton's point of view, value versus time, this is how you recover your knowledge of what the system is doing at any time t. You need to know the time and then, let's say, plot it or get a number. In Wiener's point of view, you just take amplitude, natural frequency, phase, and once you're given that, if you want to reconstruct the whole signal, you just use this formula. Yeah. So that's what's called an autoencoder in machine learning. It's just a massive compression of the amount of information that you need to have in order to reconstruct the signal in a lossless way. So you didn't lose anything if you know these 3 numbers. Now, FFT is not going to give you the phase, so you're going to lose something. It's not completely lossless, right? There are ways of recovering phase as well. All right. So the signals and systems theory develops this point of view in detail. You might have taken some courses in it. And if you look historically as to what parts of analysis and mathematics deal with this, you look at the theory of Fourier transforms and also Laplace transforms for some of the transient aspects, and that has served us in the context of control theory with transfer functions, for example, tremendously historically. You will see that in some sense, the operator theoretic approach also extends this. It's kind of this analysis on steroids, as I sometimes call it. So all of these, the reason why Fourier transforms and Laplace transforms served us really well, even when they were applied in nonlinear contexts in the past, where they shouldn't have worked as well as stated, because the starting point of these kinds of analysis is suppose your system is a linear system. Well, interestingly, practitioners have seen many times that even if you use in the context of nonlinear systems, it provides you with a lot of information. And the operator theoretic approach gives you a very comprehensive view, especially on the transient side, as to why this is. I think we understood it reasonably well, and in some of the initial books, for example, on chaos theory, there's quite a bit of discussion of asymptotic dynamics in terms of harmonic analysis. But the transient dynamics, as I said, Koopman operator theory provides you with a very good kind of unifying point of view on this. Okay. So I spoke quite a bit about this, and so now we come to the point of talking about, what is it? In the last 20 plus years, we have certainly used this approach that I'm going to present to you, that I spoke about, but didn't quite define yet. We've used it quite a bit, and we've used it in a different set of contexts, starting from modeling to analysis of data, to extraction of patterns from data, to control. It has achieved success in a variety of different applications. How did it come about? There are a few papers, the first one being that of Bernard Koopman, who was a mathematics professor at University of Columbia at the time, and a friend of von Neumann. But Koopman wrote a paper in which he observed that if you have a dynamical system, in his case, it was a conservative dynamical system that was of Newton type, you could always associate a linear operator with it. And that linear operator would be infinite dimensional. And Koopman observed that if you thought about a spectrum, think at this point, I'll describe it certainly in detail in these lectures, but think about these eigenvalues and eigenvectors, right? You have something like a matrix. So when I talk about spectrum from now on, it's not really going to be something like a fast Fourier transform. It's really, you should think about eigenvalues and eigenvectors, or we'll see that they have to be eigenfunctions. But anyhow, Koopman wrote a paper. Von Neumann realized the importance of this work almost right away. They wrote a few papers. And to some extent, some of this theory was forgotten because, well, not forgotten. It always lived in parts of the physics community, and it had large impact in part of mathematics that's called ergodic theory, that, for example, my own studies started from as well. But in dynamical systems theory in general, in applications, the geometric point of view dominated because that's what, for example, Lorentz and Ueda, to start with, and many others after them, have developed. The theory was very well developed for the geometric side already in the 80s, and for the operator theoretic side, it was applied in the context of mathematics. I wouldn't say even applied. There was a lot of work in pure mathematics that used the concepts in the context of ergodic theory. So it's only in the last 20, 30 years that we've seen a broadband applications of these ideas, and therefore, somewhat of a change of a point of view in dynamical systems theory towards this. But as I said, in conjunction with the geometrical point of view. So let's start with defining, starting from x dot is equal to f of x. This is for simplicity. Really, you could have much more general evolutions than this. But let's start with this because we have some background in it. So let's suppose that our x is on some space M. M could be, for example, a manifold embedded in Rm. It could even be an abstract manifold, but let's work with embedding in Rm, and then the point x is really just a representation of this manifold, or a vector representation of a point in Rm. So we talked about the fact that St of x0, which is called the flow, is a map that to every initial condition x0 assigns its position or condition at time t, St of x0. So this is a family of mappings on the state space M. And so now the key object is an observable. An observable is a function. It's a rule that assigns a vector in a k-dimensional complex space to a point in M, which we're right away going to work with complex observables. The reason being that when we talk about spectral properties, as you all know, eigenvalues of a matrix can be complex, eigenvectors of a matrix can be complex. Here, we're going to have an operator that is going to have eigenfunctions and eigenvalues that can be complex. And therefore, it makes sense, instead of defining functions that are only real, to start with defining complex functions immediately. And in fact, we're going to have vector valued observables. And let's denote it here by G. G itself is a static object. If I'm in state space here, then G could be, for example, just a simple evaluation of observable x1, x2, and x3 at this point. So G could be a simple vector of states, but it also could be something more complex. For example, it could be x1 squared, sine of x2, and log x3. Right? When we are given variables or observables x1, x2, and x3 that go into that vector x, there is no guarantee that that's in some sense the best description. It's a physical description. For example, in Newtonian mechanics, you can rely on position and momentum being good descriptions of the system. They might not be the simplest description of the system. I showed you the fact that, for example, in some cases, in many cases, energy is a really good observable or function to think about. And energy is a nonlinear function because it depends, even in the mass spring system, on squares of velocity and the square, in that case, square of position. So it's a nonlinear function of observables, and yet it's a very important observable. And in fact, its evolution in time is very simple. Energy doesn't change. So H dot is equal to 0, right? So there is no guarantee that when I write down an ordinary differential equation, that I have written down a very simple description of the system. I've just written a description of a system that somehow I had a physical law for. There might be patterns of exchange of energy that might lead me to understand that it's more important to understand exchange of energy in a system than really knowing where the system exactly is at. And that's the point of view adopted in Koopman operator theory. It's basically saying, let me start with some arbitrary vector valued observables. And maybe from that set, I can extract the ones that are really important. From that perspective, it's a learning exercise. So G itself is a static thing. It's just what you observe at any point in state space. This other capital G, which depends on two parameters, so G only depends on X. But this other capital G that has two arguments, T and X0, is really the observation of G that you would obtain by starting from initial condition, X0, and mapping it for time T, right? So pictorially, let's say that you have some function G defined on this space. And you have some value of G at X0. Let's say it's 1. So this G of T and X0 would be obtained by going along the trajectory, figuring out what the value of G is here, and assigning it to the initial condition. Let's say that the value of G is 2 over here. Then you would get a value of 2 at time T, right? So this thing is a time evolving or a time evolution of your observable. The simplest thing you can think about is you can say, well, okay, my X1 at this point was, let's say, 1. And now I go over here, and now X1 is -1. But you associate this with the initial condition. So at time 0, the value of X1 was 1. At time T, the value ended up being -1. So basically sitting, for those of you that have background in fluid mechanics, it's called a Lagrangian point of view, right? you're following the trajectory and kind of labeling the value of what you're observing with the initial condition. All right, so now the key moment is, okay, I have some function g, that's a function of initial conditions. As I said, that's a static object. But I can ask, how does it change in time at these initial conditions? And so for that purpose, I'm going to compose my g, which is a function, with the map st. So this is what I talked about pictorially. At x0, the value of the function at time t is going to be g observed at st of x0. And that g of st, that's called composition. So in fact, this operator here that is labeled with time t, because for every different time, I will have a different operator, takes a function g of initial condition and maps it into a function g of st of initial conditions x0. So it's a function that takes, it's a map that takes a function to a function. Therefore, it's called an operator. Note that at this point, I'm working on absolutely most general set of observables, set of functions. So if you have a function is just a rule that assigns a number, complex number to a point, or a vector of complex numbers to a point, right? So I didn't put an assumption that those functions are smooth. I didn't put an assumption that those functions have any other property than just being functions. And so I'm just monitoring how an initial function is being transported to some function at a later time. And this ut here, if I fix the time t, is called the Koopman operator for time t, and the whole family of operators labeled by t is the Koopman operator family of this system. X dot is equal to f of x. So that's how you take a dynamical system and you associate an operator. The meaning of the word operator being you take functions into functions. And so an operator is also a function, but it's just a different word, right? Because if you think about a function being a point of your space, then an operator just assigns another function with it. So in that sense, it's a mapping. But when we perform these kinds of operations on functions themselves, we call these objects operators. As you will see, it turns out to be a linear operator. And that's very nice. So in many situations, you can think about it as an infinite dimensional matrix. But I stress the point infinite dimensional. Why infinite dimensional? Well, the object that it's operating on, provided M is a continuous, some kind of a continuous space. Think of M being just a real line or a plane or even a circle or a sphere. So it's a continuous space. Then the number, the dimensionality of the function space itself is infinite, right? Because there is an infinity of functions that you can define on those spaces. Now, of course, if your original system acts on a discrete space, which wouldn't quite be possible here with ordinary differential equations, then it could become finite. And I'll show you examples in which this operator becomes literally just a matrix for some discrete systems that are discrete in space and time. But in general here, we have defined what is called an infinite dimensional operator on functions. So in discrete time, so let's talk about discrete time systems. For discrete time systems, I take some initial condition x, and I use a mapping t to transport it to x prime. Then the Koopman operator is defined as u. So it's just a one-step operator acting on a function g. Is g composed with t? So first you apply the mapping to go one step forward, and then and then you apply the composition, and this circle here denotes the composition. And in mathematics, the Koopman operator is very often called the composition operator, especially when we're talking about the context that is outside of the domain of conservative Newtonian type mechanics. Then in mathematics literature, you'll find it called composition operator. It is also interesting that actually the definition itself precedes Koopman himself a little bit. There was another mathematician that defined the composition operator itself as an interesting object before that. But certainly Koopman brought attention to this type of an object in the context of physics again, and that was an important point. Okay, so let's see, because it's easy to see in this discrete time case, that this is what is called a linear operator. First of all, if I have a flow, this ST, then put T is equal to 1, and you're going to get U1G is G of S1 of X0. So if you define this S1, S at time 1 as T, you get precisely this equation here. So you can always define discrete time operators by taking a finite time and obtaining a discrete time version. Yes, Alexander.
So, the time step that like T moves forward, is that only one in like a discrete time step, or can it be arbitrary?
Yeah, I was just about to go there. It's a very good question. What is interesting, and we will talk about this, is that it sort of doesn't matter. The reason being that any type of discretization is going to lead to objects that are somehow morphed into each other. So they might not be the same object if you took 0.5 instead of 1, but the invariants that you find, the other objects that you find, they're going to be easily morphed into each other. So they are in principle the same object, in the same way that, you know, a coffee cup is a donut, if you know what I mean, right? So it's a topological object that has one hole, right? So these objects are morphed into each other correctly. And so in general, it doesn't matter as long as your system is autonomous. So if the right-hand side doesn't depend on time. If the right-hand side depends on time, then you have a bigger problem. And there are many papers on that problem. And so there are some resolutions and some ideas on the issue, but I will spend relatively little time in the class talking about that part. Does that answer the question?
Yeah, thank you.
We'll talk more about this, by the way. So good question. So let's prove the linearity. So let's say that we take two observables, G1 and G2. Remember, these are vectors of observables defined on X, multiply them by some constants C1 and C2. This could be complex constants. G1 and G2 are also complex functions. Then U acting on this is just a composition of this new function, C1, G1 plus C2, G2 with T, yes? But if you want to evaluate this function at T of X, what you can do, since it's just a plain sum, you can evaluate separately this function on T of X and that function on T of X and multiply them with C1 and C2. And then by definition, this thing here is just U acting on G1, and this thing here is U acting on G2. So U, the operation acting on C1, G1 plus C2, G2 is C1 U acting on G1 plus C2 U acting on G2, and therefore the operator is linear. Now, if you found a linear operator, you would be remiss not to go out and ask whether it's eigenvalues, and in this case, eigenfunctions, not eigenvectors, because it's infinite dimensional. And this is what we are going to, be doing. But it's not as simple as just using MATLAB and finding eigenvalues, because remember, it is in principle to start with an infinite dimensional operator. So we're going to have to be to be smart in finding ways of reducing that infinite dimensional description to a finite dimensional one. And as I promised, I'll prove that in many different cases, it's indeed just a finite number of things that you need to know about that operator in order to reconstruct the whole operator. And that's the fun part, because that means that you have a beautiful autoencoder of dynamics that is based on an infinite dimensional object, but it really depends on finite number of or rather you can store it as a finite number of pieces of information, just like what I described in the spectral Wieners picture, right? You take amplitude, phase, and frequency, and you can reconstruct the whole signal.